This video presents declassified and licensed material of the Global Institute of Logic and Cybernetics.
To build a coherent world model, physical systems, computational networks, and governance architectures require a mathematically secure observer to crystallize reality. We often assume intelligence gathering is like setting up a passive camera, a neutral lens quietly recording data. In complex networks, this is a dangerous myth. A truly passive system has no defenses against adversarial noise. It simply absorbs whatever impacts it directly. True observation is an active, armored containment process. It requires rigorous, defended boundaries that separate signal from environmental chaos, dictating exactly what can enter and alter the system. To solve this vulnerability, we rely on an irreducible tactical primitive, the observer monad. It is the minimal lawful unit of coherent observation. This is a strictly engineered architecture. Without it, a distributed network or AI system cannot distinguish between verified memory and an adversarial spoof. It will silently hallucinate. Without this structural closure, environmental data overrides internal state. The system becomes a passive reflection of its surroundings, rather than an independent processor. This schematic lays out the blueprint of the observer monad, defining the core invariants for a secure witness. The boundary operator forms a rigid membrane, separating internal logic from external noise, dictating what data is admissible. Inside lies the internal state space, S, the secured vault holding beliefs, measurements, and memory. At its core is identity, I, a cryptographic anchor persisting across updates, ensuring the system knows what it is over time. The trace map, tau, projects the monad's internal history into the world. It outputs a verifiable, non-forgeable record of the system's decisions. Remove any single one of these variables and the structure fails. Without a boundary, the internal state dissolves into the surrounding environment. Without identity, the sequence of updates becomes untethered noise. Deploying an intelligent system without these variables leaves the network unable to verify its own past actions. Without an identity anchor or a trace map, the sequence of updates becomes an unattributable string of transitions. These combined variables establish the structural baseline for a witness. They provide the necessary closure for any agent to maintain a persistent perspective across multiple interactions. Architecture alone isn't enough. As an observer moves through time, it faces the physical threat of terminal entropic collapse. Look at this entropy gauge. External perturbations strike the boundary, and internal disorder, sigma, rises. If disorder exceeds a critical threshold, recursive continuity shatters, causing observer death. To survive, the system relies on the stabilization operator, K, an active mechanism designed to drive entropy back down. This operator normalizes the state. It corrects errors, resolves semantic ambiguity, and filters out adversarial noise, securing the monad's structural integrity before the next update. Intelligence is never a passive state of recording data. It is the continuous, active deployment of mathematical stabilization to survive time. This survival process is formalized in the recursive witness law. It is the central equation governing how a monad safely navigates from one moment to the next. The cycle works like this. Current state, stored memory, and external events map through an update function, then pass through the stabilization operator to forge a secured future state. Finally, the monad emits a clean trace segment, creating a secure historical log. Each successful cycle and the resulting trace it leaves behind mathematically proves that the monad's identity has remained continuous and intact. The observer must map its internal state forward through each update. If this recursion breaks, the monad reaches a terminal state where identity can no longer be attributed. When we pull back from the internal mechanics of a single monad, we see its movement across the vast observer configuration space. These light trails are witness world lines. They are the trace-carrying curves that observers generate as they step through lawful state transitions. The central node projects a branching influence cone, mapping lawful future paths. Behind it, the dependence cone represents the verifiable past history justify its existence. Monads actively steer these cones to avoid chaotic regions that would drive entropy beyond thresholds and destroy trace continuity. This behavior follows the principle of least collapse. Systems naturally settle into stable coherence basins to maximize their structural persistence. Observers do not wander passively through time. They actively generate causal geometry by moving only where they can securely trace their existence. These mechanics govern single entities, but we scale this architecture up to civilizational and defense-level operations by deploying distributed intelligence swarms. There is a common misconception in network design. Simply linking a massive aggregate of monads together does not automatically form a higher-order intelligence. A mere collection of nodes lacks a shared trace law. To act collectively, the system uses a braiding operator. Individual monads interact and exchange data, weaving their world lines together without violating their distinct cryptographic boundaries. If nodes interact but fail to securely log their exchanges, the system breaks. This generates ghost branches, unverified timelines, or zombie monads, which are nodes that have collapsed internally but still emit outputs, simulating witnesshood. To prevent this, multi-agent systems must strictly sequence their measurement interactions. Every exchange must satisfy braid coherence to avoid creating contradictory realities. A swarm only functions when local interactions between highly distinct, separated nodes mathematically align to produce a single, coherent global trace. The ultimate objective of a multi-agent swarm is lawful fusion, combining these braided interactions to form a massive, unified institutional monad. Fusion occurs exactly when individual nodes combine their boundaries to form a higher-order geometric witness structure, an entity whose identity is constitutional rather than individual. Look closely at the internal structure. The absolute rule of lawful fusion. The cryptographic traces of every original monad must remain perfectly preserved within the new superstructure. Erasing this internal provenance causes institutional hollowing. The collective claims consensus, but has secretly lost its witness memory. By maintaining full provenance, a properly fused institutional monad can utilize specific reflexive layers to safely model and audit its own history without triggering a paradox collapse. A civilization or intelligence swarm becomes lawful only when its witness lines braid, compose, and converge without ever losing their cryptographic provenance.